very carefully, and you are confident with all the methods of differentiation, like application of chain rule, product rule, quotient rule, etc., and of course the basic principle and the basic formulae of differentiation by now. Also, in the last lecture, we have done quite a few of the questions from the assignments and from the module exercises. So with the help of those examples, I hope you have also been able to complete all questions from the 3 assignments till now, and also from the module exercises, the questions which I've asked you to solve earlier. So let's move a little bit ahead with differentiation today and understand some applications of differentiation. Now that we have spent quite a bit of time on learning how to do differentiation, and before that on what exactly is differentiation, what we mean by differentiation, what is meant by instantaneous rate of change, interpretation of that in terms of slope of tangent, etc., and then a lot of advanced techniques in how to differentiate various different type of functions. So having done all that, now let's understand how we can use these techniques and use the concept of differentiation in solving actual physics problems, okay, or mathematics problems, as may be the case. Okay. So applications of differentiation. So, for example, the first type of application is differentiation used as a rate measurer, or something to measure the rate of change of one quantity with respect to another. Okay. So, for example, we have already seen many cases of this, that speed is equal to rate of change of distance with respect to time. Okay. But now also the rate of change of speed equals to what? It equals to what we call the magnitude of acceleration. So let's look at an example or two of the application of this concept. Okay, so we have this kind of situation. A body is moving, or a particle is moving along the x-axis or along a straight line. Such that it starts from x equal to 0 at time t equal to 0, and it reaches x equal to x at some time t. So a particle moves along the x-axis such that its x coordinate is, let us say, equal to 6t minus 2t square as a function of time, okay, where x is in meters and t is in seconds. So from this, we want to calculate various things now. So we want to find out I'll just make a correction here. Instead of 2t square, I want to make it 2t cube. Make it a more interesting example to understand. So first of all, we want to find out the speed v as a function of time. We want to find out the value of the speed at the instants t equal to 0.5 seconds and t equal to 1 second, and again at t equal to 1.5 second. So from this, we also want to find out the direction of its velocity at the same 3 times. Okay. And finally, we also want to find out the acceleration. Actually, we want to find out the magnitude of acceleration. Again, the same 3 times. All right, just take down the data of this question and try to work it out. As per the two definitions that we've written on top over here, that speed is the rate of change of distance with respect to time. Okay, and the rate of change of speed is equal to nothing but the magnitude of acceleration. Now, why we are specifying here magnitude of acceleration is because, as you know, acceleration is technically a vector quantity, so it has both magnitude and direction. So here we are only interested in the magnitude of the acceleration. Similarly, for example, velocity is a vector quantity, so it has both magnitude and direction, whereas speed is a scalar quantity, so it is a magnitude of velocity. At any instant, the speed is equal to the magnitude of the instantaneous velocity. So for example, in the second part, we are interested in the magnitude of the velocity or the instantaneous speed at these 3 instants of time. Whereas in the third part, we are interested in the direction of the velocity. So since it's a motion along the x-axis, there are only 2 possible directions, either along the positive x direction or the negative x direction. Yes, anybody got the answers yet? Very good, Parv, that's correct. very good, Tanay. Darsh, Manav, Anandita, all correct answers so far. Yes, so Parv, in the second partner, you have to understand that I have asked for the speed. Okay, so speed is magnitude of velocity. Na? So just a small matter of interpretation. Okay? So when I'm talking about speed, I will not give algebraic sign. Whereas if I said velocity, yes, I should specify the sign so that I know whether the direction is along the positive x-axis or negative x-axis. Understood, number? Yes.
Yes.
But that is, for example, giving you an idea about the third part. Because you've got the sign also for dx by dt. You've got the algebraic sign in each of the parts of second question. So that algebraic sign is giving you the idea about the direction in the third question. Okay, so let's understand the first part. So we talk about speed. It's equal to rate of change of distance. Okay. Now there's a slight technical issue over here. If the position of the particle is x, okay, then velocity v is equal to dx by dt. Okay, such that if dx by dt is a positive quantity, that means the direction is along positive x-axis, and speed is equal to v only. Okay. But if on the other hand dx by dt is negative, that means the direction is along negative x-axis. Okay. And in that case, the speed should be written as mod of, because v will become a negative quantity. So for example, in the first part, we have to be a little bit mindful of this concept. So when we look at x as a function of time which is given to us, we can see immediately that after a certain amount of time, which you'll figure out is 1 second, after 1 second, dx by dt will become a negative quantity. So given this, now we can see from here that dx by dt is obviously differentiation of this, okay, which all of you have got correct. So I'm assuming that there's no problem with this. But now if you notice this thing, now if I'm talking about velocity, it's fine to write it like this, okay. But if I'm talking about speed, I have to take care of these two cases. I have to take care of this and this. So in this, you can immediately see that dx by dt is positive for t less than 1 second. Okay, dx by dt is 0 at t equal to 1 second. Okay. And dx by dt is becoming negative for t greater than 1 second. So what this basically tells me is that if the particle starts from here at t equal to 0, it starts from rest. In fact, you can see dx by dt is 0 at t equal to 0. Then at some time less than 1 second, its direction of velocity is like this. Okay. But by the time it comes to the time of 1 second, momentarily it has stopped. Okay. And then by the time you're more than 1 second, it's actually returned back. This is when t is greater than 1 second. Just going like this. Okay. So that's why we have to understand that speed is equal to 6 minus 6t square only. Okay. For t less than 1 second. Okay. But speed becomes mod of 6 minus 6t square for t greater than 1 second. And of course, speed is equal to 0 momentarily at t equal to 1 second. Okay. So we can just generalize this by saying that, so therefore, in general, we can say that speed is equal to magnitude of velocity, okay, or mod of dx by dt. So in general, we can say, so that will work for all three cases. This is mod of 6 minus 6t square. So this will give us the correct value of speed, whether or not we are taking the time between 0 and 1 second, or after 1 second, or at t equal to 1 second. For all three cases, it will give us the correct value of speed. Okay. So just a technical matter over here, that since we're talking about speed, speed is a quantity which cannot have algebraic sign positive or negative because it's just a magnitude. Velocity, on the other hand, we will discuss about this even more detail when we come to the chapter of kinematics, which we'll do immediately after calculus. But velocity, when we talk about motion along a straight line, velocity has to be given with the algebraic sign plus or minus, so that the algebraic sign gives us an indication about the direction. Whereas, of course, if I talk about motion in two-dimensional plane or three-dimensional plane, then to specify the velocity, I have to make use of the vector notation. That is unit vectors, I cap, j cap, like that. You must be learning in vectors by now. Must have learned. Okay.
Yes,
so the technical answer to the first part is this, that you can write it as 6 minus 6t square, but you have to be mindful of the fact that the moment your t becomes greater than 1 second, it is not going to be 6 minus 6t square. In fact, it's going to be 6t square minus 6, or the magnitude of this. Okay. So this is the answer in general. Okay. So immediately you can see that for the second part, the speed at t equal to 0.5 seconds is simply, okay, similarly the speed at t equal to 1 second, 0, and the speed at t equal to, what was it, 1.5 seconds? Yes. So that is 6 minus 6 into
7.5.
okay, so this will become, okay, so 13.5 minus 6,
Minus 6, that's 7.5.
so that is 7.5. Okay. So if you forget about the mod thing, you'll remember, you'll get minus 7.5. So minus 7.5 is technically the velocity. So when we talk about speed, we should just put a mod sign on it and report it as 7.5 meters per second. On the other hand, when we are coming to the third part, okay, we have to understand that the velocity v, which is dx by dt, this gives us an indication about direction. If v is positive, the direction is along positive x-axis. If v is negative, the direction is along negative x-axis. So like I've shown in the diagram above, you can clearly understand from that diagram now that before 1 second, the direction is along the positive x-axis. After 1 second, it's along the negative x-axis. And at exactly 1 second, it doesn't have a direction of motion because it's momentarily stopped. Okay. So A part at t equal to 0.5 seconds, you can see that velocity is actually plus of 4.5 meters per second. So the direction is the positive x-axis. At t equal to 1 second, v is 0, so it's basically stopped. but it stopped momentarily. It's not going to remain at rest. That we understand. Just for an instant, it has stopped. Like when you throw a ball up, you know, it keeps going up with deceleration. Then at an instant, it stops before it starts its descent. So just for a moment, just for an instant, it's at rest. So that kind of situation is happening to this object also. And for t equal to 1.5 seconds, we saw that v is actually minus 7.5 meters per second. But actually, this was not required. Now, you've already seen that in the diagram that after 1 second, so as far as the direction is concerned, we didn't need to actually do this calculation again. It was clear before only that before 1 second, it would have been positive. After 1 second, it would have been negative. Okay, so depending on what type of quantity we are applying the concept of rate of change or differentiation to, there are some additional things like this which become important. So for example, if you are applying it to velocity, then it is directly dx by dt, so the algebraic sign also becomes important. But if you are applying it to speed, it is rate of change of distance with time. So it just becomes magnitude of dx by dt, or it becomes mod of the function dx by dt. So these kind of things we'll learn as we go along with more applications in physics. Okay. And let's come to the fourth part. So let me just check your answers first for the fourth part. Okay, people are still in the process of calculating. Anybody got the answer of the fourth part? Just take you back to the question. Okay, so let's come to acceleration. Yes, very good. That's correct. Vidhi, Manav. But again, Manav, you have to be mindful of the fact that I've asked for magnitude of the acceleration.
Okay, sir.
So we'll just take mod of what you have written. So this will become like a two-step process. First, we've got x. So this is what is given to us. So from this, we can see that therefore velocity, instantaneous velocity, is the differentiation of this. So that becomes 6 minus 6t square. And now we apply the definition of acceleration. Okay. So acceleration is that instantaneous acceleration equals to the instantaneous rate of change of velocity with respect to time. Okay, so here we will just apply the word definition. I mean the formula definition that E is equal to dv by dt. So we have got this value of v. Now we'll substitute this over here. Okay. So the magnitude of acceleration will become mod of this. So as you can see, the acceleration is minus 12t. Now the algebraic sign of this is telling you that the direction of the acceleration is negative. Okay. So for example, at t equal to 0.5 seconds, the acceleration a is equal to minus 6, and the unit will be in meters per second square. But that means that the magnitude of acceleration, that is mod of a, will become 6 meters per second square. Like this. Yeah. Now, just one additional point I will discuss about here, about the unit of a rate of change. Okay. So, for example, here x as given as a function of time, but x is in meters. Okay. So, therefore, dx by dt, okay, and t is in seconds. So, dx by dt will become in meters per second, because after all, dx is a delta x tending to 0. So, that's in meters. And dt is a delta t which is tending to 0 in seconds. Okay. So hence the unit of this has to become meters per second. Okay. And likewise now the unit of acceleration will be in meters per second or meters per second square. So in general, if we write any quantity as the instantaneous rate of change like this, so the unit for this becomes the unit of whatever y was expressed in divided by the unit of whatever x was. Because after all, it is a change in y divided by change in x. Okay. So that is a general concept of when we are applying differentiation to physical quantities which have units rather than pure numbers and functions which are unitless. This is how the system of unit works. Okay. Okay, so hopefully this is all clear. Now let's look at a different type of problem, like a geometrical type of situation. Now we were doing a couple of examples like this in the last lecture also. So we have this time, let's say we have a solid metallic sphere, and we are heating this very slowly. So just to show that it's solid, let's give it a three-dimensional perspective like this. So as you know, metals tend to expand quite a bit when we heat them. So this is a solid metallic sphere. So it's being heated slowly such that its radius, let's say r, is increasing at a uniform rate of, let's say, 0.3 millimeters per second. So per second, the radius is expanding at by a factor of 0.3 millimeters. Okay. So we want to, so at some instant of time, when the value of the radius is exactly equal to 10 centimeters, okay, we want to find the rate of change of its diameter. Okay, the diameter of the sphere is changing at what rate? The rate of change of its surface area. And we want to find the rate of change of its volume. And finally, you want to find the rate of change of its density. Because remember, as the metallic sphere is expanding because of thermal expansion, we are not adding or subtracting mass to it. It's the same amount of mass, but the distribution of mass is changing because with heat supplied, the thermal energy given to the molecules causes slight weakening of the intermolecular bonds, and that causes the material to expand. So it's not like we are increasing or decreasing the number of molecules. It's just that we are changing the arrangement of molecules by supplying more thermal energy to the system. So what is basically changing is the density. As the volume is expanding, the same amount of mass is now distributed over a larger volume. So the mass per unit volume or density will be decreasing. So when we thermally expand the material, its volume tends to expand while its mass remains constant. So its density decreases. So we also want to find the rate of change of density. Okay, so let's just work this out quickly, people. Yes, very good, Perf. Very nice. That's correct. Yeah, yes, I will, Yashovardhan, I will scroll up. Let people just take down this question, okay, and start working on it. Then I'll scroll back up once for you. Okay, very good. Muskan, Jitendra, Parv. Okay, so I'll just scroll up for a moment. Some people wanted to probably write this part. Yes, Yashuvardhan, this was the part you had to write down, the fourth part, or okay, now let's come back to this question. When a question like this is like application of rate measurement by differentiation, but at the next level. Okay, what we have to do is we have to basically use chain rule kind of concept. Okay. So for example, for the first part, we know that diameter at any instant is equal to twice of the radius. So let's write diameter with capital D so that symbols don't become the same. So the diameter, okay. So it's very obvious from this that the rate of change of diameter will become 2 times the rate of change of radius. And the rate of change of radius, this is the instantaneous rate of change. With respect to time t, that is given to us as whatever 0.3 millimeters per second. So the rate at which the diameter will change will become 0.6 millimeter per second, and this is also a uniform rate of change. This changes uniformly with respect to time. Okay. So it doesn't matter whether we are looking at the instant when the radius is 10 centimeters or 20 centimeters or whatever it is, the rate at which the diameter is growing is the same. It's going to be 0.6 millimeters per second. Okay. Whereas when we come to the other quantities here, we will see that it's a variable rate because it depends on the radius also, right? So for example, in the B part, we can see that the surface area, suppose we denote it with the symbol S or A or whatever, it is, as we know, 4 pi r square. This is the surface area of a sphere. So this is like an instantaneous surface area because R is instantaneous. So understand over here that R is an instantaneous quantity. So what we mean by instantaneous quantity is that it is variable with respect to time. It means it changes with time. Or in simple terms, what we call time varying. Okay. So accordingly, the surface area S is also an instantaneous quantity. It's not constant. It changes with respect to time. So now we want to find rate of change of surface area. So that becomes rate of change of 4 pi r square. Okay. So in that 4 pi is a constant, so we can bring that out. But then we are left with rate of change of r square. So this is where we now use a chain rule step. That this is equivalent to 4 pi into differentiation of r square with respect to r into dr by dt. Okay. So differentiation of any function with respect to t is the same thing as differentiation of that function with respect to r into dr by dt. So this is our chain rule. So that is over here. And here this function is nothing but r square. in this particular example. So the formula for the instantaneous rate of change of surface area therefore becomes 8 pi r into dr by dt. Okay. So at the instant when r is equal to 10 centimeters, okay, and dr by dt is of course 0.3 millimeters per second uniform. Okay. The rate at which the surface area is changing. Now again, this is where we have to be careful in units. This is in millimeter per second. So better to convert this to millimeters. So this is 100 millimeters. Okay. So it is 8 pi into 100 into 0.3. So this will be in millimeters. This will be in millimeters per second. So the unit of this that we'll get, 8 pi is a dimensionless constant or unitless constant. So we'll get 30 into 8 pi. So that is 240 pi millimeters square per second. That is the rate at which the area is changing. Okay. Or we can also write this as 2.4 pi centimeter square per second. Yes, you had a question?
No,
Siddesh?
sir. I was just saying that I solved it in centimeters.
Okay. So same thing, na? You got 2.4 pi?
Yes, sir.
Yes. Okay. And we can leave the answer this way, or we can also substitute pi as approximate value 3.14. Okay. So that way we can get a more exact answer also. But for now, this is fine. Okay. We can leave the answer either this way or in the other unit of centimeters square per second.
Sir,
Yes.
sir, but 1 mm is 1 mm
0.1.
is
0.1. Na? So that's why 1 mm square is 0.01. Na?
yes, sir.
So that's how. No? So 1 millimeter square is 10 raised per minus 2 centimeter square. So 1 millimeter square per second is also 10 raised per minus 2 cm square per second. So that's how I've done the conversion. So hope this one is clear to all of you. Please go through the steps very carefully once. Okay. I've tried not to skip any step and do every step in detail. Okay. Still, if something is not clear, please let me know. I will explain again.
Sir, it should be 0.024 centimeters square per second, no? Because
Okay.
1 centimeter is 100 millimeters and centimeter square, so that's 10 raised to 4 millimeters square.
Sorry, Beta, can you just be a little bit louder? Darsh, I can't hear you.
Sir, it should be 0.024 centimeters square per second, right?
0.024.
Because
Why,
1
Beta?
centimeter
See,
square
1 millimeter is how many centimeters?
100. I mean, 1 by 100. 10 raised
1 by 10, no? 1/10. So 1 millimeter square is 100th, no?
Sir, 1 by 100, right? 10 raised to minus 2
Ah,
milli So
so that's why in centimeter square per second, see, 240 pi is becoming 2.4 pi, isn't it? Understood, no?
yes, sir.
Okay.
I made it.
Yes, Priyam, you want me to scroll up to the A part, is it?
Yes, sir.
Okay. So the A part is quite straightforward because diameter is just double of radius. So the rate of change of diameter will just become, when you differentiate this 2 is a constant. So twice the rate of change of radius. So whatever is the rate at which the radius is increasing, the diameter is increasing at the rate of double of that.
Yes, sir. Thank you, sir.
So for example, at some instant of time, if the radius was 10 centimeters, the diameter is 20. Now 1 second later, the radius has increased to 10.03 centimeters. So the diameter has increased to 20.06 centimeters. So how much the diameter is increased by in that 1 second? 0.06 centimeters or 0.6 millimeters, like that. Okay, let's come to yeah, Yashovardhan, I know you got disconnected, so just after the lecture, when I send the recording and the notes, just cover up the portion that you missed out. So if you have any doubts, you can let me know later. Okay. Some more things. Okay, D part. Okay, I'm coming to that. Okay, so let's deal with the third part first. So we can see that the volume is 4/3 pi r cube, where again we understand that this is the instantaneous volume, how it is changing with time, because the radius is also changing with time. So now the rate of change of the volume with respect to time, this will become differentiation of this whole function 4/3 pi r cube. So the same process. Take this outside, then make this differentiation with respect to r into dr by dt. So I've just applied the chain rule directly. Okay. So this becomes 4/3 pi into 3r square into dr by dt. So this formula for instantaneous rate of change of volume with respect to time becomes 4 pi r square, that is the surface area actually, into the rate of change of radius. This becomes the formula. Okay. So at the instant when r is equal to 10 centimeters or 100 millimeters and dr by dt is 0.3 millimeters per second, the rate of change of volume okay, or we can also write this as 4 pi into 10 square into centimeter square into 0.03 if we write this in centimeters per second. Okay. So the rate at which the volume is changing is millimeter cube per second, or that is the same thing as simply 12 pi centimeter cube per second. Yes, that's correct. Okay. Om and Sambhavi, Jitesh,
Yes, sir.
correct. Okay. So this is the instantaneous rate of change at the moment when r is 10 centimeters or 100 millimeter. Now comes the slightly tricky part, the density. Okay. Density in physics sometimes we refer to with the symbol rho, which is the same symbol as resistivity, which you might have studied in current electricity, but since okay, so the density equals to mass per unit volume. So over here it is m upon 4 by 3 pi r cube. So we can say that density as a function of the radius is 3m by 4 pi into r to the power minus 3. So this is density as a function of radius. So again, the rate of change of density with respect to time will become rate of change of this function with respect to time. So that will become derivative of this function into dr by dt. Chain rule, that concept will apply here. So instantaneous rate of change of density will become instantaneous rate of change of 3m by 4 pi into r to the power minus 3. So by chain rule, so this is so to get the rate of change, we also need to know the mass of the object. So this is a general formula. So at the instant when r is equal to 10 centimeters, okay, dr by dt is equal to 0.3 millimeters per second. And suppose mass m is something, is suppose 20 kilograms. Let's assume. Okay. Okay. So that's given to us in the question only. So in this case, interest noticeably we'll get the rate of change of density with a negative sign. Let's write this like this. Okay. So we can see, we can also, for example, write this in grams, which will make it a more familiar unit of gram per centimeter cube per second. This will become the rate of change of the density, with of course the additional information which I had not given originally, that the mass of the sphere is 20 kgs. Okay. With that additional information, otherwise those of you who have given the answer in terms of m, that's also correct.
So, can you show how can we, I did it by this way, density is mass upon volume now. So I
Yes.
took mass as constant, so it will be, density will be dy by dt, so mass will be outside and 1 upon v. So I took v raised to minus 1, then I solved it. So I'm not getting the right answer, please.
Okay, so I'll just show you that you will get the same answer, either calculation mistake there or calculation mistake here, one of the two. So let's just check out. Okay, so in terms of m, what we are getting this as, we are getting this as, okay, minus 9m upon 4 pi r to the power 4 dr by dt. Okay. Now, if I write this in terms of this, now remember what was my dv by dt? It was this.
Yes, sir.
Okay. And what was my volume? It was 4 by 3 pi r cube. Okay. So I'll have to express it that way now. Okay. So let's calculate this value first. Then we'll put the same value in the other method that you have used. Okay. So ये कितना आ रहा है? This is coming with the mass taken as 20 kgs. This is coming out to be, let's just calculate it. So this is how much now? 9 into 27 divided by 2 pi. Okay. Into 10 raised power, it will become 4 and 4 goes away. So 10 raised power minus 2. Okay. So this is what I am getting. 27 by 2 pi into 10 raised power minus 2 gram per centimeter cube second. Okay, just check my calculation once.
Yes, sir.
Okay, now supposing I use this, that density is mass upon volume, or mv to the power minus 1. So rate of change of density is equal to m into, rate of change of this. So I can write that as m into, this is the method you applied, beta?
Yes, sir.
Okay, so this will become minus m by v square into dv by dt.
Yes, sir.
Okay. So now let us see what we'll get from that. Now here I will substitute m as 20 kg. Okay. Now at the instant when r was equal to 10 centimeters, what was our volume? So it was 4 by 3 pi into 10 raised power 3 cubic centimeters. Okay. And what was our dv by dt? So for that we'll have to go back above and check out what was our rate of change of volume. It was this much, 12 pi centimeter cube per second, right?
Yes, sir.
So 12 pi cc per second. Okay. So we'll have to substitute these two values here now. We have to substitute this value and this value here. So on substituting, so this is rate of change of density. So on substituting this, we will get this as minus of 20 into 10 raised power 3 grams divided by this volume squared. So that is going to be 16 pi square by 9 into 10 raised power 6 in cubic centimeter square. Okay. And into this volume rate, which will be 12 pi in cubic centimeters per second. So I think it should give you the same thing. Definitely it will give us the same thing. So 9 into 20 into 10 raised power 3 divided by 16 pi, I'm cancelling this pi, okay, into 10 raised power 6 into 12, and this will be grams cc per second divided by cc square. So this will be gram per cc second, correct?
Yes, sir. Yeah, got it.
So it is coming the same, no? So it's just a matter of like the correct substitution. So in general, so this is also a equally all right method of doing the question. Okay, because since we've already, the only thing is in this you have to separately calculate the volume and substitute, whereas in the earlier method I had to just substitute the value of r.
Yeah.
dv by dt I had anyway calculated, so I'm not doing any extra calculation there. Okay, so people, hope this question is clear. By both the methods where I've expressed density in terms of R first, okay, and use dr by dt, or I've expressed density in terms of volume V and use the value of dV by dt we calculated earlier. Okay. So both are equally valid methods. But as you can see that in a calculation like this, sometimes things get a bit complicated when you are substituting. So you have to be very careful, especially careful about the units you are substituting in. Make sure you don't make a mistake in the application of differentiation formula, etc. Also, like all these things are important. Okay. All right, now let's move on to another interesting type of situation, okay, of application of differentiation as a rate measure. So in trigonometry, you would have understood the concept of angle of elevation, right? So if you have a point like this and you're observing from another point like this, then with respect to your horizontal line of sight, if the line of sight of that point P makes an angle theta, then this is called the angle of elevation for the point P, okay, as seen by the observer. Okay. So obviously different observers will observe different angles of elevation. So somebody else is here, so they will see a different angle of elevation. Okay. Somebody is closer, they'll see a larger angle of elevation. Okay. And of course, angle of elevation is always with respect to the horizontal. So we have to assume over here that gravity is acting in this direction, and this is the horizontal plane. So let's look at an example based on this angle of elevation concept. Okay. So now in our particular numerical problem, what is happening is that there is a particle which is at this particular instant of time having a downward speed, or you can say downward velocity of, let's say, 15 centimeters per second or 1.5 meters per second. Now also, the observer that we're talking about, his eye level is at a distance of d equal to, let us say, 20 meters. Okay. And at this particular moment, this distance, this height from this point, this happens to be 15 meters. So at an instant when the height OP is 15 meters, okay, the speed at which the particle P is falling is 15 centimeters per second. So we want to calculate the rate of change of theta, that is the angle of elevation, from the point A, let's say. This is the point A where the observer is present. So what is the rate at which the angle of elevation theta is changing? And we want to find the rate of change of the distance AP, which is S. Okay, rate of change of the distance S, which is basically the distance, instantaneous distance of the particle P with respect to the fixed point P. Okay, so this is a fixed point. This observer is not moving, but that particle is falling freely. So at a moment or at an instant when the speed at which that particle is falling is this much, and the height of that particle from the horizontal plane, that height OP or Y, is equal to 15 meters. What is the rate at which the angle of elevation is changing? So first of all, can you tell me, should the rate of change of angle d theta by dt be a positive quantity or a negative quantity?
Negative.
You can see it will be a negative quantity, you know, because for this right angle triangle OAP, you can see that the perpendicular y will be decreasing, whereas the base d will remain constant. So as y is decreasing, so is theta decreasing. So the algebraic sign with which we should write d theta by dt should come out to be a negative quantity, first of all. Okay. Now, how we will find this d theta by dt? By using differentiation as a rate measurer and using the concept of chain rule. Okay, I know y is changing with respect to time because y is that height. Okay, so I know dy by dt. So from that I have to generate the value of d theta by dt. So that means what I have to do? First I have to find theta in terms of y and then use the chain rule. So theta depends on y and y depends on time. So from that I can find the rate of change of theta with respect to time. That is the type of approach we have to take in this type of problem. Just try this out, people. Okay, so just to give you a hint in this, there are a number of options that I have of expressing the relationship between theta and y. So basically from here I can see that the quantity y is decreasing with time at the rate of d. So basically we can say that dy by dt is in fact minus of 15 centimeters per second at the instant shown. So the minus sign here is very important. because y is decreasing at the rate. So accordingly, we can see s is also decreasing. Okay, and theta is also decreasing. Okay, so ds by dt should also be a negative quantity, and d theta by dt should also be a negative quantity. Okay. But the question is exactly how they are related to dy by dt. Whereas we can understand that small d equal to 20 meters is a constant. That is not something which is changing with time. Okay. So y, theta, s, these are all instantaneous. Okay, or they are variables. Whereas d, this is the fixed quantity. So conceptually, this is what we have to focus on. The constant. Okay. No, so Janendra, you have to use the chain rule here. Na? So what we can understand here that for the first part, I want to find d theta by dt. Whereas I know that dy by dt is equal to minus, I know this, I know the value of y is 15 meters. I know the value of small d is 20 meters. So how will I find this relation? So I have to express theta as a function of this thing of y, and then use the fact that d theta by dt will become so this is what I have to use. This is what I have to calculate. Okay. So coming back to that diagram, this is y. This is d. So moment later would have become like this. So anyhow, so you can see that we can express y by d as tan theta, or but I'm going to use this notation because this is basically what we call tan inverse function. So don't worry about this just now. We will study this later. So that's why I'm leaving out this. I'm going with this method. Okay.
So we have done inverse of tan.
Sorry, come again, Vita.
We have done inverse function of tan.
You've done inverse function in trigonometry, right? Okay. So yeah, but you know, in differentiation, we'll come back to inverse function a little bit later. Okay. So right now, let's go with this only. So we can say that tan theta is equal to y by d. So that means differentiation of tan theta with respect to time is equal to differentiation of y by d with respect to time. Okay, so this is all right, this step, right? Now we use chain rule. So differentiation of tan theta with respect to theta into d theta by dt just becomes on this side 1 by d into dy by dt. Okay. So this is the chain rule step here. Okay. So what is differentiation of tan theta?
Sec square theta.
Very good. So sec square theta into d theta by dt is equal to 1 by d into dy by dt. Okay. So on the other side, what will happen is that d theta by dt will become cos square theta by d into dy by dt. Now go back to the diagram and you can see you can write cos theta as this. Okay. So if y was 15 and this was 20 and this therefore becomes 25. So at that particular moment, cos square theta is 20 by 25 or 4 by 5 whole square divided by d, which is 20 into dy by dt, which was how much? Now the unit thing becomes important here. Okay. So remember, this is unitless. Cos theta is a unitless quantity because it's a ratio. But in the denominator, this 20 is in 20 meters. And dy by dt was minus 15 centimeters per second. Okay. So my d theta by dt, this will become minus of 4 by 5 whole square. Okay. That is 0.8 square. So 0.64 into 15 by 20 is 3 by 4. So 0.75. But now it is centimeters per second divided by meters per second. So I'll make it 10 raised per minus 1 per second. Because this is like centimeter per second divided by meter is equal to so 10 raised per minus 1 second inverse. Okay, so that's how this unit has worked out. And that's where this extra 10 raised per minus 1 has come from. Okay, so 3/4 of 0.64 will be 0.48, right? So minus 0.048 radians per second. This will become the rate at which the angle is changing.
So,
Yes.
sir, but 1 meter is 100 centimeter, right?
Oh, sorry, my mistake. Yes. Absolutely correct. So this is 10 raised by minus 2, in fact. Let's make that correction here. This should be 10 raised by minus 2. So this becomes an even smaller number. The angle is changing at a very slow rate, as you can see. So this becomes minus 0.0048. Radians per second. Is it correct now?
Yes, sir.
Getting the same value now? Yeah. Okay. So basically, whenever we express an angle in SI unit, it is nothing but in radians. So this thing of saying that the angle is changing at the rate of n second inverse is actually, what is that? It is radian per second. In vectors, you have studied about, as part of vectors, you must have become familiar with the angles 37 and 53, right?
Yes, sir.
So you can see that this angle theta at the moment is how much? It's actually tan inverse of 3 by 4. So it is 37 degrees. So the angle is 37 degrees, but it's reducing at a very small rate of 0.0048 radians per second. You can also convert the radians per second into degrees per second by multiplying by a factor of 180 by pi. you can use this factor that x radians is equal to these many degrees.
Sir,
Yes.
what if the viewpoint or the source of the eye is also moving with respect to the
Oh, then
point
the
of the
problem becomes
duration?
very interesting actually. Then instead of small d, that quantity will also have to be taken as a variable, and then we will have to use a more complex kind of approach. We'll have to see how we use combination of product rule, chain rule, etc. So suppose this guy is also moving, okay, and this object is also falling. So this is falling at v1, let's say, and this guy is moving at v2, let's say. So then what is happening? If I take this distance as x, which is a variable, and this distance is y, both are changing with respect to time. Okay. So my theta is such that tan theta is equal to y by x, where dy by dt is how much? It is minus v1, and dx by dt is also minus, but it's minus of v2. So now I'll have to use this, that rate of change of tan theta is equal to rate of change of y by x. Okay. So this will become sec square theta d theta by dt. Now this we'll have to differentiate this. So denominator into differential of numerator minus numerator into differential of denominator divided by denominator square. We have to use this. Understood? Huh?
Oh, okay, sir, perfect. Yes, sir.
So the question becomes that much more complex. Okay, but still it's this only. Okay, so it becomes cos square theta into x dy by dt minus y dx by dt divided by x square. In this itself, you can see that if you take x as a constant, then this second term disappears. So you're back to where we started. If x was a fixed quantity d, then this reduces to what we have got now. It reduces to cos square theta divided by d into dy by dt. This reduces to this.
Yes.
It's the same thing.
It's the same thing. But this
So
is
we
like a
can
more
solve the first question with this method as well, right?
yes, exactly.
Okay, sir.
It reduces to this. Okay. So, for example, when we come to the subject of mechanics, okay, there will be a lot of situations like this where we have different objects which are moving, and we have to calculate the rate of change of distance between them, or the rate at which the angle of projection or something is changing. So we have to use these kind of relations there. Okay. Now let's come to the second part. How is the distance changing with respect to time? So we have to find the rate of change of the distance between these two. Okay. Now, of course, I'm going back to taking this as a stationary observer. Technically, I should take the vertex of the triangle where his eye is located, but I'm just doing a bit of approximation here. So here the easy thing to do would be, since I know dy by dt, I know y and I know d. So what I have to do is I express s as a function of y. So then directly I can find ds by dt as the derivative of that function into dy by dt with chain rule. Okay. So as you can see, s is equal to square root of y square plus d square. So ds by dt will become this into dy by dt. So you can see that this will become, now differentiation of this, again we have to use chain rule. So this is 1 upon 2 times square root of y square plus d square into dy, into 2y into dy by dt. So that is actually equal to y by s into dy by dt. And y by s is nothing but the instantaneous value of sine theta. So this happens to be 3 by 5 into minus 15 centimeters per second. So this distance s is changing at the instantaneous rate of minus 9 centimeters per second. So at this particular moment, the object P is coming closer to A by a factor of 9 centimeters per second. The distance between P and A is decreasing at the rate of 9 centimeters per second. So this step, again, chain rule has been used. So already we use chain rule once over here. And then again,
Sir, will you explain the differentiation in when you applied the chain rule?
sorry, will I apply?
When you applied the chain rule, can you explain the differentiation once again?
This one, this one, the differentiation of square root of y square plus d square, this one?
Yes.
Okay. So I want to calculate differentiation of square root of y square plus d square with respect to y. Okay. So what I'll do is I'll take y square plus d square as z, right? So square root of root z with respect to y will become square root of this. Got it now?
Okay, sir, clear.
So this is, okay. So further this step, it just becomes into not dy by dt but into 2y. So you're differentiating with respect to y. So in this, I just skipped these steps and directly I substituted this here.
Sir,
Yes.
sir, will these kind of sum also come in the Sunday's test?
Yeah, I mean, simple level of rate measurer questions will come. Okay. Not very complex ones like this one, but like the volume and surface area type of ones that we did earlier. And
Okay.
more it will be concentrating on the methods of differentiation, like application of chain rule. Okay. I mean, basically what we did till about last week, that thing is going to have the major weightage in the test coming, right?
So find the slope of the tangent at this point, and those type of sums can come in.
That's a little bit louder, please,
Uh,
beta.
Find the slope of the tangent at.
Those kind of questions definitely. Given a function, find the slope of the tangent at a given point, or just directly find the derivative of the function. Application of product rule, quotient rule, trigonometric formula, exponential, logarithmic, all these things. Okay?
And when is the function increasing and decreasing? That type of question.
Yes, yes.
Okay, those are okay.
Okay, now next thing we will see in application of differentiation. So these were some examples of application of differentiation directly to find rate of change. So differentiation used as a rate measure. Now differentiation can also be used to understand the behavior of a function. So let's talk about what we mean by how we can look at the behavior of a function. So further, as applications of derivative or differentiation. So this is something which we are, you can say we are back to pure maths. That how differentiation is being used in maths to understand the behavior of a function. And of course, if we apply that function in a physics problem, it's going to help us solve the physics of that situation also. So ultimately, that's how it's relevant from physics point of view. So behavior of a function y is equal to fx from its derivative f prime x. What we can come to know about the behavior of the function. So this is going to be purely conceptual now. Okay. If we suppose assume that the graph of a function is looking something like this. We have some kind of an arbitrary function whose graph is like this. So you can see that, let's say the starting point from where we started plotting the graph is A. Now up to this point B, let's say B is the point that I've drawn exactly where the graph reaches the peak. And then it starts to dip again. And then it dips all the way, let's say up to this point C. And then after C, it again starts to rise till the last point in the graph that I've drawn. So this is a graph of some function y equal to fx drawn for the interval. So this symbol is x belongs to the interval a to d. Okay. Where this type of bracket, as you might have studied in maths, is called a closed interval. So this basically means that x is greater than equal and less than equal to d. Whereas if we use a normal bracket instead of a box bracket, it is an open interval where the equality is not included, is greater than and less than if we use a normal bracket. Okay. So anyway, that's not so important. What is important for us is what I'm going to discuss next, is that if you draw a tangent at any point like this between A and B, you draw a tangent, you can see it has a slope which is positive. If you draw a tangent at any point like this also between C and D, you can see its slope is positive. Right now, we don't know the formula of the function. So we might not be able to calculate how much the slope is, but definitely we can tell that the slope is positive. Whereas if you look at any point like this, which is between B and C, you can see that the slope is negative. Now, if you correlate this with the behavior of the function, what it is showing you that when I'm in that region of X, where I'm going from A to B, the function is increasing. That is, the Y coordinate of the function increases when I increase the value of the X coordinate. Whereas when I come between B and C, the opposite happens. We call the function as a decreasing function, or the nature of the function we say is decreasing for the interval between B and C, because the value of the Y coordinate is dropping as we are increasing X. So wherever we can see that the function has a decreasing nature, the slope of the tangent is negative. So this becomes an important thing when we are thinking of the reverse, that we don't know the graph of a function, we just know the formula of the function, and we want to find out in which region of the domain, that is in for what values of X, the function is increasing, or for what values of x the function is decreasing, we can use this concept. So what we can see from above, that derivative of the function f prime x is positive for x belonging to these intervals a to b, and again union with c to d. Okay, or we can say x being greater than equal to a and less than b, union with x being greater than c, less than equal to b. Okay, so the important thing is that in an interval, in any interval of x, if the derivative of the function is positive, it implies that the function is increasing in that interval. So over here, what this is implying, this implies that the function fx is
Positive.
increasing, or you can say y increases with x for these intervals, for x belonging to a to b union with c to b. Okay. Now there's one critical point here. Why I have not included the point b? Because b is the point at which the function has gone and peaked like this. So if I draw the tangent exactly at the point b, assuming b is the point where it has exactly peaked, the tangent will have a zero slope. So that is why it is not, b is not included in this condition, that the slope is positive. Okay. The slope is positive right up to b. If I take a point which is infinitesimally close, that means b minus dx wala point b hai, even there the slope will be negative. Sorry, the slope will be positive. Even here the slope will be positive. But right at the point b, the slope is actually becoming zero. So that's why we have not included b in the interval. Now it is less than b. Now you might ask what we mean by less than b. Up to what point I should go? Should I go up to 0.01 less than b, or should I go up to 0.001? So there's no answer to that, because the number line has infinite real numbers between any two real numbers. Okay, so technically I can go up to b minus dx, where dx is again delta x tending to 0. But the point is I should not include b in that set of values of x where f prime x or the derivative is positive. Now, similarly, the reverse of this, if the derivative is negative in an interval, that means we know the behavior of the function in that interval is such that the function is decreasing. So just make a quick note of this point, or make sure you understand this point, then we'll start applying these in particular functions to understand it better.
So,
Yes, tell me.
sir, here round bracket means excluding, right?
So that is a, okay. I'll write that point separately down later. Okay. So just like this means, so this is a closed interval. So separately, open interval is given like this. If we say, it means that x is greater than a and less than b. And like that, we also have mixed interval, where one side is open and one side is closed. So for example, if I write this one, a to d, this is a mixed interval. So this is x is greater than equal to a but less than b. Okay, so these are just about intervals. They're just about different types of intervals: mixed interval, open interval, closed interval. Is clear now?
Yes, sir.
Okay, so just as we have seen, the implication that when derivative is positive, it means that the function is increasing. Now, similarly, derivative f prime x is negative for this interval now. Again, I'll write it as an open interval because I don't want to include b and c, or x greater than b but not including b, and less than c not including c. Okay, so this implies that the function fx is decreasing in, or you can say decreasing for that interval. So that's one thing about the behavior of the function. Okay, so in short, we can write like this, that f prime x is positive implies that the function is increasing, and f prime x is negative implies that the function is decreasing.
So this will help us find if a function in a particular interval is increasing or decreasing, right?
Yes. Okay. Or for a given function, it will also tell us that in which interval the function is increasing and which interval the function is decreasing. So,
And
for
it can
example,
be
I
for
have no
any
idea
set
about
of
the,
values.
yes, yes. So I have no idea about the graph of a function, but I want to try and understand something about the behavior of the graph. Okay. So I can make use of this. So, for example, suppose I have this function y is equal to x cube minus 3x. Okay. Now I don't know the graph of this function. I can of course plot it in the traditional way by drawing various points and all that. But instead of that, I just want this information, that I want to find the intervals of x for which y increases, okay, or decreases with respect to x. Okay. So in this, all I have to do is I have to understand that the given function is x cube minus 3x. So the derivative of the function dy by dx or f prime x is how much? It is 3x square minus 3, which I can write as 3 into x square minus 1, which I can write as 3 into x minus 1 into x plus 1. So now I can see that the derivative is positive for, that means x square should be greater than 1, or x should be greater than 1 union with x is less than minus 1. Or we can say that x belongs to the interval minus infinity to minus 1 union with 1 to infinity. So now I can say that, okay, in this interval, I know that the function will be increasing. So for this interval, the function fx is increasing. Whereas less than 0, So for this interval, the function is decreasing. So now to answer this question, I can see that the function increases for x belonging to these intervals. And the function decreases for x in this interval. So as far as this particular question is concerned, this is all I have to do. I have to find the intervals. So I've done that. This is my final answer. But if I correlate this information that I've got with a little bit more stuff, okay, then that can also help me in further analyzing the function. Now, suppose I want to plot the graph of the function. Now, let's see how this information is going to be useful for us. So let's say I want to plot an approximate graph for this function y is equal to x cubed minus 3x. So let's analyze how we'll do that. Okay. So we can see that first point, for x tending to minus infinity, what will be the value of y? It tends to minus infinity. So for example, because x cube term dominates, for example, if I take x as minus of 10 raised power 3, that's minus 1000. Now y will be approximately minus of 10 raised power 9. Actually, it will be minus of 10 raised power 9 plus 3000. So it will be slightly less than that, but it's approximately equal to this one. Okay. Whereas similarly, for x tending to infinity, the value of y will tend to infinity. Because if I take x, for example, as 10 raised power 6, which is 1 million, a very large positive number, y is
Raised to the
approximately,
power 18.
yeah, sorry, x to the power 18, not 12, that's correct. Okay. It's a very, very large number, you can see. It's only slightly less than that. Yes. So that's one thing. Okay. Then I can see, for example, now see, I'm going to keep in mind these intervals. So -1 was an important point for me. 1 was an important point. Okay. So let's check out some values before and after that also. So for now, let's take some table of values. So for x equal to -3, for example, how much you're getting y is?
Minus 16.
Minus 27 plus 9.
18 minus.
So that is minus 18. No?
Yes.
Okay, let's check at -2 what we are getting.
0.
So -8 plus 6.
Minus
How much
2,
that
2,
is?
2.
minus
Minus. Okay. So let's check at 1 what we are getting. Sorry, -1. So that's -1 plus 3.
0. Correct.
-1 plus 3 is becoming how much? Plus 2, isn't it? Okay, let's check at 0 how much we are getting. We are getting 0. Okay. Now let's check at 1. Should again get 2. Sorry, we should get minus 2. Okay. Let's check at 2. We should get plus 2 this time. Is it?
Yes,
Yeah.
sir.
And let's check at 3. It's a symmetrical type of function, So we should
18.
get this as plus 18. Okay. So this is there. And then in addition to that, we also have the information that if I think in terms of number line, the function in this part of the number line, it is increasing. Then in this part, it is decreasing. Then again, in this part, it is increasing. So that together with these values, if I put together all this information, I have enough ammunition to at least draw a rough estimate of the graph, how it's going to look. Okay. So let's do that next.
Sir, a curvy N, right?
It will be curvy. Okay. But we have a little bit more idea about the points which are significant for the curve, where it is turning and all that. We have some information about that now.
Sir,
Yes.
I just disconnected for 1 minute. 1 minute. What were you saying?
Sorry, come again, Beta.
Sir, I was just disconnected for 1 minute. What were you saying? Yeah, from your own.
Oh, here we for the last minute we just looked at the values of x and y. These ordered pairs for this function. So just substitute the values of x as from -3 to +3, and correspondingly we got these values of y. Okay.
Okay, sir. And sir, did you tell the students to leave because there were like about 60? Now they are in 30s.
No, I have not asked the students to leave. It's okay.
Okay, sir.
Okay. It will be another 5 minutes before we finish the class. Okay.
Yeah, sir.
Okay. So now let's start looking at the values. So let's start with 0. At 0, the value of y is 0. Okay. Then at 1, the value of y is -2. So if this point is 1, this is 100 or something. Okay. Here is. Okay, so at 1, the value is -2. So okay. Then at 2, it is again jumping to +2. Okay. And by the time you're going to 3 is much larger. It's +18. Okay. And by the time you go to 100, it goes off the charts. Okay. Now similarly on this side, at -1, it is +2. Okay. At -2, it was -2. Okay. And at -3, it was -18. Let's say this is like this or something. Okay. Now we also know this, that it should start from -infinity. Okay. And it should increase all the way up to what? Up to -1. So the function has an increasing nature till we reach -1. But after that, what should happen? The function should start decreasing till we reach the value of x equal to +1. So in this part of the domain, from -1 to 1, the function should be like this. And then again, it should be increasing. So my graph is a little weird looking here, but better drawing of the graph would be something like this. Say like this, okay, where this value is where it changes behavior. Before this, it was increasing. After this, it's decreasing. And again, this value is where it changes behavior. Because before 1, it was decreasing, and then again, it starts increasing. And then, of course, you can see that if 2 is somewhere here, so you can see by just analyzing few values, few key values, and analyzing the behavior of the function. This was the important thing, that the function was increasing in this domain from -infinity to -1. Then again, the function was decreasing between -1 and 1. And then again, the function was increasing from 1 to infinity. So that gives us a lot of useful information, apart from few values which I've analyzed.
So the sign of the derivative is also important, right?
Exactly. The sign of the derivative becomes very important to me, where it is positive and where it is negative. You know? Okay, people. So hope this is clear.
Yes, sir.
Okay, so we'll conclude here. I will be giving you another assignment this week, which will be to do with application of differentiation as a rate measurer, and also more practice with chain rule and the previous things. Okay. Now, just to give you a heads up about what we'll be doing in the next lecture. Next class, we'll also be understanding that when you look at the general graph of a function like this, if the function peaks and then starts dipping, and then again dips and again starts peaking, then the point at which it reaches this peak, this point is called a point of local maxima. So we'll see the proper definition of what is local maxima of a function, and we'll see how to use differentiation or calculus to find the local maxima of the function. Similarly, we'll see that if it dips and then again rises, so the point exactly where it changes its behavior from dipping to rising, that point is called the point of local minima. So we will see the concept of local maxima and minima of a function and application of differentiation or application of derivative to find that out. So that's one of the things we'll see in the next class. The other thing we'll also see is something called second derivative, okay, of a function, and how to make use of that also. So for a function y is equal to fx, this is what we call the derivative. Okay. But if we differentiate it once more, we get a quantity which is called the second derivative. So second derivative is given this kind of a symbol, that it is differentiation of the derivative, or it is differentiation of f prime x. Or therefore in short form it is also called f double prime x. So for example, if you have the function y is equal to x cube, then the derivative of the function is 3x squared, and the second derivative of the function is, so second derivative is given this kind of a symbol. It basically looks like d square y upon dx square, this quantity. So it is nothing but differentiation of the derivative. So that in this case is differentiation of 3x square. So that is 6x. So for this given function, this is the second derivative. Okay. So the second derivative is 6x, whereas the derivative was 3x square. So we will learn more about second derivative, and more importantly, the significance of second derivative and how that also helps us in understanding local maxima and minima, etc. Okay. So that's it for today's session, people. Hope you have all understood more or less the things we've discussed. Please revise the lecture carefully, okay, and try out the assignment questions as always. Okay. So that's it. Thanks for attending and wish you all the best.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay, bye, people.
Yes, sir.
Thank you, sir.
Hi, sir. Thank you.
Okay, people, bye. Sambhavi, if you're there to answer your question, no, that particular graph does not have a particular name. Okay, it's just a cubic functions graph, unlike parabola, which is the name for quadratic function.